So thank you so much. So it's a great privilege to be here. I'm thrilled to see this full room. I'm honored to collaborate with OCULUS for about 20 years now. And AI detection for optimized diagnostics with ultra-high resolution OCT images and beyond. My consultant for OCULUS beyond that, I have the Ambrosio Vision Academy and Brain, which are relevant disclosures. But my main disclosure is doing my best for the patient. And I remember when I saw the Academy in 2004, actually 2003, the first version of the Pentacam. And 10 years later, passed in 2012, we see this golden Pentacam. And the Pentacam family has grown for multimodal. We have axial length with the PCI, axial length with Hartmann check wavefront sensor. And that is continuing to turn with the Pentacam OCT, which I believe is a true corneal biopsy, is an optical biopsy, is a non-contact optical biopsy. Words matter. I start talking to the patients that I do in my consultation of optical biopsy, and patients are afraid of not going there because they think I will cut the tissue at the consultation, but it's a non-contact optical biopsy. So the Scheimpflug is still there, and there is synergism, as there is synergism between clinicians and scientists, engineers, industry, and hospitals. Synergism is very important. And synergism because we have an unprecedented resolution of 1.9 microns or even less. The Pentacam Cornea OCT is a spectral domain with a broad bandwidth of 200 nanometers and gives you a wide angle paracentric scan. So it covers beyond limbus to limbus. And this information takes the same time as the rotating Scheimpflug. So it's simultaneously. So you take the Scheimpflug and OCT utilizing the rotating scan so that you can cover all the data of the cornea in a very nice fashion. So we combine this work on OCT and Scheimpflug for a true optical biopsy. It's in vivo non-contact optical biopsy, and we published that last year. So if you don't look for, you don't find. But if you don't have the capability to see, you won't be able to resolve what you are looking for. So we have to be keen on what we are looking for. And it's like turning the light. Andreas Scheinmiller, he was one of the first to say it's like turning the light. So you have the Scheimpflug image, and with the optical biopsy, you have this type of information. And you see the amount of thickening of the epithelium, the amount of scarring, and that is very important for therapeutic refractive surgery, which goes beyond not over-treating repair cases that we all cause as refractive surgeons. Keratoconus treatment, corneal dystrophies, scars, those are the patients that will benefit the most, and there's a huge unmet medical need. So for many years, we look at this in the textbook, the epithelium, the basement membrane of the epithelium, the Bowman's layer, the stroma, the interior stroma, the posterior stroma, the decimus layer, the endothelium, Dua's layer. Now we can see in the level of the histology. And how to make the clinical use of these high-resolution images. Too much information makes more confusion than clarification. So you need to be keen on using that data. How to turn this as a standard, as something that you need. The solution is definitely using AI. Artificial intelligence is fundamental. So we have multimodal refractive diagnostics. For example, keratoconus and ectatic corneal disease. We have a plethora of data that start from anamnesis up to genetics that we still don't have. I really believe that we will go more and more into the molecular biology domain, but we need to apply AI. Artificial intelligence applied along with ancient intelligence. So we have to understand the whys so that we have the hows and eventually to go beyond. The A2I at the third level includes applied artificial intuition and beyond human limits. I work with a group of multidisciplinary group that started with my friend João Marcelo Lira and Aidon Machado. And this is a very important slide because when we define AI, a lot of people think about ChatGPT or other metric or platforms. They are great. They help us a lot. I use ChatGPT to find the best route from the metro from my hotel to the center. It helps. But it's not designing devices that has our capacities, like asking a great agent, but it goes beyond the human, beyond but not over. Interestingly, the work from AI in ophthalmology, maybe medicine, was pioneered by topography. Steve Skly's group with Maeda and Mike Smolek, they started the neural network classification of corneal topography. And I have a clinical case for you. This patient is a male, 23 years old, has a normal topography based on AI, a little bit of high asphericity if you may want to pick up something, but this patient had a high D, and I told them not to do surgery, that I would not to do surgery. It was in a Zoom call with colleagues from Iran, and many of them are here, Professor Sadgad and his team. And then, interestingly, I told them, if you have a Corvus data pre-op, that would be even more interesting. And we had, and the TBI V1 and TBI V2 are displayed here. So we are talking about ectasia susceptibility. This is not keratoconus. Topography was normal based on objective AI data. So you have to go beyond the front surface data so that you understand the interesting thing. And we are launching in the meeting the BEAS, the Brain Enhanced Ectasia software that integrates the intrinsic susceptibility of the patient based on tomography, if you have Pentacam data, the DV4 with an interesting approach for making it from 0 to 1, along with the RTA, the relational tissue altered, which is a metric that is in a relational. For example, if you hit something that is very weak, the same force will cause a different damage if you hit something with the same force, something that is strong. So it has to be relational, and it goes to the relation of age and thickness. And of course, the flap cuts more fibers than the ablation. So it's relational. In the future, we will integrate definitely models with finite elements. But we have cases that the technology should help us. So we have tomography, biomechanics, we are solving all the issues, but we have very asymmetric ectasia cases with a normal topography, normal tomography, normal CBI, great work by Ricardo Vinciguerra for analyzing with AI, with a linear regression model, the data for having a Corvus biomechanical index, and even normal TBI. What about the epithelium? We have that question to solve, and I hope next year we will have enough data with colleagues from India, Roger Shetty and his great team, so that we collaborate with Ricardo Vinciguerra and others, so that we collect a database with epithelial thickness data along with tomography and biomechanics, so that we can see how much improvement we get using that data. So this is an interesting situation. Is a patient that has asymmetric ectasia, 2015 in the left eye and 2020 -1 in the right eye, 55 years old. And you see the epithelial thinning, even though the epithelium is not thin. That's very important. And thinning and thin are different. For example, we can have a 40 micron epithelium, which is thin, that is not thinned. It's important to understand that difference. So relational thickness for epithelium is the way to go. And my colleague and friend Dan Reinstein, who is a great saxophone player besides a great surgeon, I would trust my eyes to him. He has a great quote that the epithelium reacts. And just based on his loss of epithelial healing, cornea epithelium has an ability to compensate change. It, by definition, is not the first thing that happens on the pathophysiology of keratoconus. It feels depressions, it thins over the peaks, it has a change according to the stromal change and the rate of curvature change, and that's interesting. And if you want to measure anything, the very first thing is, how can I trust this data? I can trust this data looking at repeatability. And with the new segmentation that Abhijit Sintaroy, colleagues from Bangalore, did a great work to collaborate with OCULUS R&D, we have the segmentation of the tear film. So the conventional epithelial thickness map and the epithelial thickness map without the tear film is very important. You see the epithelial thickness along with the tear film, along with Bowman's layer, stromal thickness, and eventually endothelial data as well. So this is going to help us with the epithelial thickness, with the segmentation. So in a study with 40 healthy participants, turning innovation to standards, the epithickness map validation, the repeatability was already very good. I presented last year, very similar to Solix and MS39. Now we have, it's even better. It's less than 1 micron in the center, because we have the epithelial thickness. And if you look at the images, you see the brightness of the tear film. And when you remove that, that's what you're removing. So it's getting higher and higher standards of quality. So it's less than 1 micron on the repeatability. We also can see things that our eyes cannot see. So when you do this, the AI very quickly finds what's abnormal on the scans. So you find this is abnormal basement layer, and there's a scar there. So that saves us time, makes us more efficient and more efficacious. So this is going to be displayed in very nice software so that we can use in the clinical data for making planning. So there are a couple of very special presentations. This is a very subtle epithelial thickness from a 72 years old gentleman that has had some change in his refraction, no cataract. Epithelial thickness can change that, and AI will help you to understand that. And the second case, a 57 years old that also has very subtle abnormalities, and this can be related to recurrent erosions. This will be very important if this patient comes as a candidate for laser vision correction, because if I cut a flap or a smile, I have a lot of chances of having problems related to the epithelial slough, because the adhesion of the epithelium is not normal in that situation. So this will be displayed in different innovations. So the AI anomaly is a great project led by Sven Reisdorf, that you see scars, you see endothelial changes. We just saw a patient at the booth that everything was relatively normal, and he has a little bit of change on the endothelium, and they said, here you have something abnormal. I don't know if it's a false positive, but he said, oh, I was diagnosed with Fuchs dystrophy, but he doesn't have edema. And eventually this can lead to prognostic on which patients you should do cataract surgery, which patients you should advise to do a transplant along with cataract surgery. We will use this technology to have important questions solved for enhancing our clinical decisions. For the AI solutions, we have worked, for example, for quantifying the meibomian glands with a K5 with beautiful infrared images, and this will help us to even further improve our ability to do tear film and ocular surface treatments. So this is something that is very exciting. AI detection for optimized diagnostics is here to help us. Beyond primo non nocere, which is do no harm, AI will help us if we do the proper questions, empower efficacy, efficiency, so that us, clinicians, can serve better our patients. It's not to replace us. The clinical relevance and the standard of care for enhancing safety is there, but is to empower us to be better clinicians. So don't be afraid about AI, but learn how to use it. Simple tasks, how to get the metro to get here from there. Very easy. But at the clinical day, you'll be more efficient and more efficacious. It's different to be replaced, to be empowered, and even more relevant. Integration and synergism is key, and I thank you so much for your kind attention.